So, hello, my name is Michael Buster, and I'm a driver engineer from Imagination Technologies. And I'm here today to talk to you about how using specifically command methods and pipelines, but indeed all of Vulkan, allows applications to provide more information up front, so to allow implementations to not have to rely so much on the guesswork or heuristics like they would have to on perhaps a more traditional API. And this is really important, because while heuristics gets you most of the way there, and it covers the vast majority of use cases, there's always going to be some applications that fall foul of the driver's guesswork and end up on the dreaded slow path. So by using Vulkan, you can get a lot more predictability. But obviously you can also get a lot more performance, as Tom's alluded to. And in my presentation, I'm not going to be talking so much about GPU performance. Instead, I'm going to concentrate on the CPU, which is what command buffers and pipelines are designed for. So we're both going to look at single-threaded efficiency, as well as how command buffers, and to a lesser extent pipelines, allow applications to exploit multiple threads when they're writing their applications, which, as you know, is critical in the modern CPU landscape. It's not just about performance, and it's not just about predictability. It's about battery life as well. If you can maintain the same performance in a Vulkan application that you had in your OpenGL application, but do so at a significantly lower CPU cost, you're going to be more friendly on your battery, and that's pretty important because you don't want people burning holes in their pockets. So this thing doesn't work.
Click the right button.
It wasn't focused. There we go. Oh, that's good. So what are command buffers? Command buffers are a deferred list of commands that you are going to submit to the GPU for later execution. And that's the key difference between Vulkan command buffers and the types of commands you would send in OpenGL. In OpenGL, it'd be ignore display lists because they're pretty grim. Everything's immediate. There's no difference between recording a command and submitting a command for execution. They're intrinsically entwined. And from a driver's point of view, this is really painful because all the driver sees when it's implementing an OpenGL or an OpenGL driver is the application saying, do a draw call, do a draw call, do a draw call, and how many more draw calls are going to come? The driver has no idea. It can't predict the future. What types of draw calls are going to come? What are those draw calls used for? The driver has absolutely no idea. So this is a really big problem. And I'll give a very, very oversimplistic example of the types of issues you could run into when trying to implement a more traditional API. So we know we're going to be accepting commands from the application, and we need to ship those commands off to our GPU for execution. Now, we don't want to just take each individual command and submit that to the GPU, because there's an inherent overhead, both on the CPU and the GPU, submitting commands to the engine for execution. So we're going to have to buffer up some commands, we're going to have to batch them. So internally, we're going to implement a command buffer. And how big are we going to make our command buffer? Well, let's take an arbitrary decision and say our command buffer has space for 50 commands. Now, the first application that we're going to run comes along and gives us 5 commands. So we'll record those 5 commands into our command buffer, but we don't want to submit our command buffer for execution yet because we know that there's inefficiency if we submit empty or under full command buffers. The problem is if that application doesn't send any more commands, when does that work get scheduled for execution? Well, who knows? It's most likely going to get submitted to the GPU due to that command buffer being flushed by some, at least according to the application, unrelated command that it records. And this is pretty bad because you get unpredictability, and it might not be the worst for performance, but you'll see hitching and lag, and the application starts to mistrust the driver. On the other hand, the second application comes along, and now it sends 50,000 commands to the driver. Well, we only have space for 50, so what we're going to do is we're going to fill up our command buffer, submit it to the GPU, and then repeat 1,000 times. And this is also bad, because like we said, there is a slight overhead both on the CPU and the GPU to submitting command buffers. And yes, there are many ways in which drivers can go to solve these issues, and the problem is these are all clever ways, and they're heuristics. They work most of the time, but they don't work all the time. Vulkan solves this by separating the act of recording commands from the act of executing those commands. So now when an application says record this command, the driver doesn't have to worry how many more commands are going to come. The application is going to tell the driver when it's finished recording commands. So the driver can concentrate on just creating the most efficient command buffer for that set of commands. And there's a whole bunch of other benefits to this separation that we'll see as we go through. So Tom mentioned descriptor pools. There's also an equivalent command pool. Now, I said before that we've removed all the guesswork from Vulkan, That's a little bit of a lie. While the driver is recording the command buffer, it still doesn't know how big that command buffer is going to be. And there is some overhead in the bookkeeping to do with calculating how much resources command buffers own. So instead we use the command buffer pool, and what the command buffer pool does is allow an implementation to amortize the cost of allocations in a command buffer over multiple command buffers. So rather than storing all this bookkeeping and overhead information per command buffer, we can instead store it on a command pool and share the load. Command pools also allow the synchronization. So again, there's slight overhead to bookkeeping the threading model. And instead of putting that burden on every single command buffer, you're going to have far more command buffers than you're going to have command pools, because you can have far more command buffers than you can have threads. So by putting this on the pool, we just reduce the cost of having to repeat everything on different command buffers. Now, pools are also interesting in that they own all the resources for all command buffers that have been allocated from that pool. What this means is you can reset a pool and instantly reclaim all of the resources that have been allocated for all of those command buffers. And there are certain types of applications that might batch all their command buffers for a single frame into a single pool. And once that frame's finished, they want to free up all the resources for all of those command buffers. Now, rather than going through one by one, the hundreds of command buffers, they can instead go to the pool and reclaim all their resources. If you do want to be able to reset individual command buffers, you have to opt into that behavior when you create a command. And this is a common theme throughout Vulkan. You opt into behavior if it's more restricted, if and only if you need it. If you don't need to individually reset command buffers, don't set the flag that allows you to. If you don't set the flag, the driver can do a much better job if it knows it's only ever going to be dealing with group reset rather than individual reset. Now, like I said, command pools provide very lightweight threading context. So what was the problem in OpenGL? Well, the way drawing works, and I've said single thread OpenGL context here, yes, like Tom alluded to, there are shared contexts in OpenGL which do allow a limited form of multi-threading, but there are still pretty big limitations on shared context. You can't have multiple threads concurrently recording commands which are drawing to the same FBO. And also there's a huge amount of driver overhead in making the magic of shared contexts just work, so they're not a real answer. The way OpenGL works is, inside the driver there's a ledger, or a book. And whenever you bind a bit of state, or change a texture, or do pretty much any state operation, what you're doing is you're updating that ledger to record the latest bit of state. When you come to record a draw call, or in OpenGL submit a draw call, what the driver does is it looks at that ledger and it says, well, I need all of these bits of state, so I'm going to take it from here and then bake that into my draw call. Now the problem is, since we only have one ledger for the entire context, you obviously can't have multiple threads which are all updating or reading from that ledger at the same time, because they would trample on each other. In Vulkan, that state update, that state information, is held on each individual command buffer. What this means is, if thread 1 is recording to the first command buffer, it can mutate its own set of state. Then thread 2 can record to a different command buffer and update a different bit of state. And this allows us to have as many threads as we want, recording to as many command buffers as we want. So I put thread n here, but really you're probably going to want to limit that either at startup statically or with a max thread count. And it's most likely you're going to want about as many threads as you have CPU cores, unless you want to reserve some for other behavior. Now, before we said the limitation on pools is that you can't have multiple threads concurrently recording to the same command pool. What this means is, if thread 1 and thread 2's command buffers came from the same command pool, the application would have to synchronize between those threads, which is not what we want. So instead, you have n threads. What you'll almost always want to do is create n command pools. Each thread gets assigned a command pool, and then will only work with command buffers which belong to that thread's command pool. And it sounds more onerous, but it's actually really easy to work with, and it works really well. So now that we know why we want command buffers, the benefits of command buffers, and the fact that we can go in parallel, which is great, what do we actually put into these command buffers? Well, we put different commands into command buffers. That's not the slide I should be on. There we go. We put different commands into command buffers. So I've missed out one type of command, which is state setting. Now, state setting isn't really a command that gets necessarily executed on the GPU. It's more of a command that just updates this ledger I was talking about inside the command buffer. So I've skipped off this slide because it's not really a GPU command. So we've got synchronization, and I don't want to go into that because that's the subject of the talk, which Tobias is going to be walking us through. We have compute commands, which are currently dispatch, and direct. They're exactly what you'd expect. Graphics commands, which are a little bit special due to render passes, and graphics commands are things like your draw commands, your subclass management commands, as well as clearing attachments and a few other different commands like occlusion queries and whatnot. Finally, there's transfer commands. And transfer commands are probably a little bit more interesting for this talk, because if you come from an OpenGL or an OpenGL-esque background, a lot of the work that transfer operations do are hidden from you quite significantly. So, what are transfer commands? Now, I've lied on this slide, there's a typo. Transfer commands are almost always raw copies, apart from when they're not. And the exception to this rule is blitz image, which does allow you to scale an image. But largely speaking, transfer commands are commands that copy memory from one place to another. The special thing about transfer commands is they can change the tiling of an image. Now, I don't have time to go into exactly what image tiling is, but I'll give a very brief overview. In Vulkan, there are two types of images. There are optimally tiled images and linearly tiled images. You almost never want to use a linearly tiled image. The use cases are quite niche. If you know what you're doing and you really need to use one, great. For the most part, only ever use optimally tiled images. In fact, on many implementations, there are really severe limitations on linear images. So in Power BI, for example, you can't have bitmaps on a linear image. You can't have image arrays. I don't think you can do 3D. Only ever use optimal images. You don't want to use anything else. So the first type of transfer, which is probably the most important, is transferring data from the CPU to the GPU. Now, this isn't necessarily from your CPU memory to your GPU memory, but this is from CPU visible memory into GPU-only memory. The reason you might want to do this is if you've got a Titan Fury X or whatever they're called sitting in your PC at home, you're going to have some static data in your scene. So let's say static mesh data. You're going to write it once from the CPU when you load your application, and you're never going to change it again. The CPU will never touch that data. Which means you want this data to be in a memory which is as fast as possible for the GPU to consume. You don't care about the CPU's access to that memory. Unfortunately, on quite a few different types of discrete cards, the fastest GPU memory might not necessarily be visible to the CPU. So how do you get your static data into that really fast memory? Well, you create a staging buffer in CPU visible memory, you write your buffer data into it, you then allocate your buffer in GPU visible memory, that really fast bit of memory, and then you create a transfer command which transfers from the slow CPU only access once memory into that really fast access multiple times memory. And this is the type of thing that those terrible, terrible usage hints in OpenGL try to imply to the driver, but let's not talk too much about them. This stuff is hidden from you in OpenGL. It's now the application's job to do. Now, you might think, well, if I'm on a SOC or a UMA system, I can see all the memory that the GPU can see, so I don't care about these transfers. Well, that would be true if it wasn't for that aforementioned image tiling. The only way to write an optimally tiled image is to use the transfer command. This is because different implementations have a different view of what an optimally tiled image is. So while you might be able to physically access the memory, you don't know what the meaning of the bytes in that memory is. So what you have to do is, again, create a staging buffer, write your linearly tiled image into the staging buffer, then allocate the optimally tiled image, and transfer from the staging buffer to the optimally tiled image. Similarly, if you want to read back from either a buffer, which is in this special GPU-only memory, or you want to read back an image which is currently optimally tiled, you'll have to do the same thing in reverse. Again, create a staging buffer in CPU visible memory, and then queue a transfer that pulls it back from this GPU optimally tiled format back into the CPU in a linear format. Now, the final class of transfers is really interesting, because this is GPU to GPU transfers. Strictly speaking, all of these are GPU to GPU, but this is when the CPU is not involved at all. We're not generating any data on the CPU. It's all from the GPU and consumed by the GPU. Now, the first type of GPU to GPU transfer, which is interesting, would be pipelined updates of data. What this means is, if you have a command buffer referencing data in a UBO, like Tom mentioned, you're now responsible for synchronizing access to memory. And that includes CPU to GPU synchronization. So while the GPU is referencing data in a buffer, you can't go and write that on the CPU. The driver's not going to stop you and you're going to get undefined results. What you can do is you can create a staging buffer that has the new data in it. You can upload your commands, and then you can queue a transfer task, which will happen after your first set of draw commands have finished consuming that data, which will update the data in the UBO. And then you can submit the same set of commands again, which are going to run, but with new data back in it. So that's a pretty good way to do reuse command buffers and reuse them with a different set of data backing. The other really important use case is MIPGen, where you would queue up a series of VK command lit images to generate your mipmaps. There is no VK command to generate mipmaps. It's up to the application to do. So we said before, graphics commands are special. And why are they special? Well, they're special because they have to go inside a render pass. And the opposite of that is true. A command which is a non-graphics command is not allowed inside a render pass at all. And exactly what a render pass is and why we have these limitations, Andrew's going to be covering. But for the moment, all you need to know is graphics commands have to go inside a render pass. There's another limitation. Render passes have to be in one command buffer. You can't begin a render pass in command buffer A and then end it in command buffer B. And you might be thinking to yourself, well, this is quite a severe limitation, because before we said the way you exploit multiple threads is by creating multiple command buffers and compiling them all on multiple threads. Now, the problem is, if you've got mainly graphics work, and in a lot of applications, the bulk of your work will be draw commands to the same scene. How do we split this up over multiple threads? Well, we do have an answer, and that's called secondary command buffers. So a secondary command buffer is very similar to a primary command buffer. You create and interact with it in exactly the same way. You just pass a flag when you start it to indicate to the driver that it is in fact a secondary command buffer. Now, the difference in usage with the secondary command buffers is you never execute a secondary command buffer on the GPU directly. You never submit it to the queue. Instead, what you do is you execute that secondary command buffer in the context of a primary command buffer. Think of it as a function call, and you can just call that function over and over again. But there are two rules that govern secondary command buffers. The first rule is you can only put commands inside a secondary command buffer that would be legal to execute where you execute those secondary commands. So if you're going to execute commands inside a render pass, your secondary command buffers are only allowed to contain graphics commands. If your secondary command buffers have non-graphics commands, they're only allowed to be executed outside of a render pass. But what this does do is it allows us to get around the limitation from before. So we've got one single big scene that we want to record a whole bunch of draw calls to. We can split that scene up over a bunch of secondary command buffers on multiple threads, record them all concurrently, and then bring them back together and execute them inside the same render pass. Now, the second rule of secondaries is you'll notice that I'm doing the same state operations, these grey boxes on the bottom, in both sets of secondary command buffer. There is no state inheritance or state leakage from primary command buffers to secondary command buffers, or from secondary to secondary or secondary to primary. So you can't inherit any state other than the frame buffer attachments. The only time you don't have to re-record a secondary command buffer is if you're recording the same set of draw commands but to a different image of the same format. But other than that, you have to rebind all the state independently in each secondary command buffer. What this means is you probably want to achieve a balance between creating too many secondary command buffers, which gives you much finer-grained control over dispatching work to multiple CPUs. But you don't want to make them too small that the overhead of doing the bind operations in each secondary command buffer counteracts the benefits of creating more fine-grained control. The secondary command buffers, primary command buffers to a lesser extent, also bring up a really cool technique in Vulkan, which wouldn't really be possible in a traditional API. And that's command buffer reuse. So if you've seen the demo outside of GNOME board, then this is exactly what I'm explaining. If you've not, it's in the demo room and you can look at something, I'm sure. Effectively, what we do is we split up the scene. We split up the scene into a whole bunch of sections. I would say tiles, but tiles is not a nice word. And then we frustum check those tiles or sections against the camera. Any tile which is currently in view, we put onto a task queue, and then we have a whole bunch of threads which are going to pull tasks off that queue and record a secondary command buffer that contains the draw calls required to draw just that individual section of the scene. We then submit the primary command buffer, which has all the secondary command buffers within it, and it goes off and is drawn. Great, so we've used multiple threads. What would be better than that? Well, on the next frame along, we're going to move the camera, and unless you're interested in making your users or players sick, you're probably not going to move the camera that far, especially if you're going at 60 FPS or higher. So the camera's moved a little bit. What this means is the majority of the tiles which are in blue here are actually exactly the same tiles that were in view last frame. The red tiles have gone out of view, so what we can do is we can reset these command buffers. And this is an example of a case where you would want to be able to individually reset command buffers rather than doing a group reset. So we can reset the red command buffers and reclaim their resources, because we don't want to use more and more memory. The new command buffers which we require are in green, correspond to these green tiles. So we can put the green tiles onto our task queue, threads all those tasks off, create secondary command buffers, and we can re-execute them. But all of those tiles in blue, which is the majority of the tiles, they're the same as last frame. Yeah, we update the UBOs so that they're in a different position, the camera's changed, but largely speaking, they're the same. So if I go back and re-record them, we already have them from the previous frame. And indeed, we can do that in Vulkan. We can take a command buffer we've recorded previously and re-execute it as many times as we want, as many times as it's valuable. Now, there is a spectrum of applications where, on one side, like Gnomeboard, it's really easy to take advantage of this. We take advantage of it for basically every draw call in the scene. There are going to be some applications on the far end of the spectrum where they're not going to be able to take advantage of this at all. It's simply not possible. But most applications are going to fall somewhere in the middle. So, for example, if you've got a bunch of static geometry and some dynamic geometry, you might want to think about partitioning the scene by static geometry, recording command buffers for that static geometry, and then special casing the dynamic geometry and recording that every frame. So, to a greater or lesser degree, different applications can take really good advantage of command buffer reuse, and that's the #1 way to get CPU efficiency. It's far better to do no work at all than it is to do a little bit of work really fast. So if you can use command buffer reuse, and you can architect your application to take advantage of it, I strongly recommend you do. Finally, just a brief word on lifetimes. Tom's already mentioned most of this. When you allocate a command buffer, until the point in time you submit it, that command buffer belongs to the CPU, it belongs to the application. So you can do whatever you want with it. You can record into it, you can reset it, you can free it. That's basically the only operations you can do with it. However, once you've submitted it to the GPU, it now belongs to the GPU. It's not yours anymore. Don't touch it. Undefined things will happen, and the API will not stop you from touching it, but if you do, something will almost definitely break. Now you can wait on that command buffer until it's completed on the GPU, and once it has, now it's in the CPU domain again, and you can do whatever you want with it. So now that we know command buffers are great, they allow us to use multiple threads, they reduce CPU costs, what do we actually put inside command buffers other than those draw commands? Well, that state I was talking about before is really important, and pipelines are, at least in my opinion, the most important concept that Vulkan introduces for reducing frame hitching and unpredictability across implementations, and even within an implementation. So what are pipelines? Pipelines are a whole bunch of stuff, an immutable bundle of stuff, and that's the difference between OpenGL and Vulkan. In OpenGL, you can GL enable this, GL enable that, GL blend func this, blah, blah, blah. You can tweak little knobs, all at a very fine granularity. The problem with this is pipelines are built after a whole bunch of things, and in OpenGL, we're building on a legacy where everything was a fixed function state, and then we slapped programmable shaders on, and then we slapped resources on top, and then we slapped more dynamic state on top of that. And it was all a bit of a disaster, really. So it's these fixed function states that are actually the cause of all of our problems. See, the dirty secret of a lot of modern implementations is many of these fixed function states, and this differs across implementations and it might differ within a vendor even. Many of these fixed function states are actually implemented as shader code, which we either append or prepend or interleave into the programmable shader stages that an application provides. Now the problem with this is the application doesn't, in OpenGL, you don't provide the fixed function states at the point in time you compile your program. You just provide the shader strings for all the stages and then link them together. What this means is, in an implementation, let's take Power BI for example, we do color blending in shader code. So you create your program, but you've not given us the blend code. Well, what we're going to do, we can't fully compile the shader at that point in time. We can certainly do some work at shader create time, but not all the work. Instead, what's going to happen is we have to wait until we see the full set of states that contribute to the shader code before we can actually do that final step of compiling all the way down into the most optimal hardware code. And this manifests as hitching, and it's the worst thing in OpenGL and OpenGLES. You've written your game, and your player is walking down a corridor, your frame rate's great, 60 FPS, they're loving it. They turn around the corner and pull out their torch, and now you want to activate your really fancy stencil shadow and shadow volume effects and balloons and whatnot, because they've got their new lighting effect out. But from the driver's point of view, this is the first time it's ever seen this combination of shader plus all the fixed function state. And it's going to stall because it's going to have to go off and recompile some shaders, because this is the first time it's ever seen these shaders being used in such a way. Now the players are annoyed because their frame rate's tanked. The developers are annoyed because on their system it might have worked better, and they don't think they're doing anything wrong and just changed some states. That's what the API is for. The API lets me do it, should I be able to do it? And all the time the driver is happening off compiling GLSL. And this is awful. So the reason we have pipelines is we take all of that state that could possibly contribute to a pipeline recompile, and we bundle it up into one immutable object. What this means is the point in time that the application asks the driver to compile the pipeline, the driver has all that information, and that's the time it can actually compile the pipeline. So when you call VK create graphics pipelines, the driver is not going to not create your graphics pipelines at that point in time. It's going to do what you say, when you say it. And by doing so, you're going to remove a whole load of unpredictability from your application, not to mention horrible frame pitching. So what are these fixed function states? They're all the stuff from OpenGL. There's nothing new added. It's basically everything that isn't a descriptor layout or a shader. What about things that are shaders? Well, we've got some shader status, same as OpenGL. Computers and on here, compute pipelines are slightly different from graphics pipelines. Largely similar, but they only have a single shader stage. Bear in mind, tessellation and geometry aren't in every single implementation. They're not required by the API, but they are in the core API. And the cool thing about shaders in Vulkan, as Neil's going to be talking a lot more about next, is they are in a binary intermediate format, which I'm not a compiler person, I don't know anything about dominators or graphs. What I do know is there's a massive pain when you're implementing a driver and you're implementing a GLSL parser, because we're going to implement it slightly differently from another implementation, and there's a whole load of variability. So SPID is great for removing that variability, again, between implementations. We have the descriptor layout, and I think Jesse's going to be talking a lot more about this, but I'll just give a terrible analogy instead. So what's a descriptor layout? Well, if we consider a UPO in OpenGL, when we compile our shader, we don't have to pass a UPO that we're using exactly for that shader. Instead, in the shader code, we write a interface layout block, which doesn't describe the contents of the UPO, it describes the types of the contents of the UPO. Descriptor layout is almost identical. It doesn't contain the resources that the shader or the pipeline is going to use, it just describes the types of the resources that the pipeline is going to use. And the reason we require this when you compile the pipeline is so that the implementation can make sure that the pipeline it compiles is compatible with any descriptor set that has been created from the same descriptor layout. Which is important for fast switching pipelines without having to rebind resources or vice versa. Finally, if I told you you had to recreate a pipeline for every time you change stencil state, you would probably tell me, well, you would ask me what I'm smoking, and then you wouldn't use the API, because that would be quite frankly terrible. There are obviously really valid use cases for changing state draw by draw. Classic example, you're doing stencil shadows, you want to change the stencil ref value every single draw call. You don't want to create a new pipeline for every single one of those. So there is some dynamic state involved, but it's important to know it is opt-in. By default, it's static. But when you create your graphics pipeline, you can declare to the implementation that you want some states to be treated as dynamic. And the reason that you want to explicitly tell the application, the implementation that states is dynamic, is if it knows the state doesn't need to change draw to draw, which is much of the time, it can create a significantly more efficient pipeline. So only create dynamic state when you do actually need it to be dynamic. The final piece of the pipeline puzzle is the cache. Now, since we're going to be creating far more pipelines in Vulkan than we have shapes in OpenGL, the reason for this, we've baked a lot more state into the pipeline compared to a shader in OpenGL. So we're going to have an explosion of pipelines, which potentially could be bad for memory. So we have a pipeline cache object that aims to mitigate the pains of having too many pipelines. It's a really simple object from the application's point of view. Basically, you pass a handle into a compile, and the implementation will first, before compiling the new pipeline, check to see if there's any information in the cache that it can reuse for the current compile. If it does generate any new work from the compile, it will write that work back to the pipeline cache, so any subsequent compiles can leverage that work. The pipeline cache is also the mechanism by which Vulkan allows you to load and store shaders. And by the way, this works way better than an OpenGL with shader boundaries, Because we have more information when we create the pipeline, what we write out to disk is significantly closer to what we need when we load it back in again. So you can't load and store pipelines individually, you just load and store the cache. So I think I'm out of time, and I'm also out of slides, which is a pretty good coincidence. So thank you very much for putting up with me. I don't know if there are time for questions. One or two questions.
Yeah, one question. In terms of abstraction level, are OpenGL and Vulkan pretty much the same level, or Vulkan is at a slightly lower level?
Vulkan's significantly lower level. There are far fewer abstractions.
Significantly lower.
So things like the transfer commands in OpenGL, when you upload a texture, you just say upload a texture and the texture gets uploaded, and in Vulkan you have to store that yourself. For example, that's just one example amongst many.
All lines have been unmuted.
Anyone has a question on the...
Just one question.
If the ownership of the pipeline changes to the GPU when you submit it, the ownership of the command buffer, can you reuse command buffers in subsequent draw calls or subsequent frames?
Yes. So remember, you can resubmit it as many times as you want. There is a flag that you have to opt in to do this. Again, it's opt-in, so if you don't need to do it, don't do it, because the implementation can do something more efficient. There's something called simultaneous use. So if you set the simultaneous use on a command buffer, you can submit that command buffer while it's already in execution. You can't do anything else. You can't reset it or reuse it, but you can submit it multiple times. So, and if you do need to use simultaneous use, then set a flag. If you don't just set the flag to be lazy. That's the story about the whole of Vulkan. There's a whole load of opt-in features that make tailor the API to your use case. If you don't need that feature, don't set it, because the implementation can do something faster.
Thank you.
Sorry. So just on that, is it always slower to use the simultaneous use tag, or just on some implementations?
So the question that I don't think that came through, but is it always slower to use simultaneous use? No. It'll vary across implementations. It shouldn't really ever be faster to use simultaneous use. Well, I'm struggling to think of a situation where it could. But it might be slower on some implementations. Like with everything, test it. Test across every implementation you care about running on it. You really have to do that.
Cheers.
Please put the mic.
Can you write command buffers on the GPU?
So currently, no. There's exploratory work. I'm sure that people are doing to enable things like that, but there's nothing like NV command list.
So you cannot do executing direct.
So you can't do?
You cannot do something like the executing direct extension.
You can't do executing direct. You can get close. You can create a command buffer. You can create a command buffer that exclusively contains draw and direct calls, and then basically null out all those calls by setting their instance count to 0, which is not as efficient, but it gets you most of the way there, if that makes sense.
All lines have been unmuted.
Any questions on the conference call bridge? Okay, no questions.
All lines have been muted.
So yeah, thank you very much for putting up with me. I hope all of you at least took one tasty morsel out of this smorgasbord of the session. And I'm now happy to hand over to Neil, who will talk to you more about Sphere V. He is a compiler person who understands combinators.